Hey, this is Ken Roser, and we're going to talk about the remainder theorem. Um, with numbers, it's true that when you divide one by another, one of two things will happen. Either the number you're dividing by goes in evenly, or the remainder goes in evenly, the remainder is zero. Same thing, right? Um, and when the divisor goes in evenly with no remainder, both the resulting quotient and the divisor are said to be factors of the dividend. Or when the divisor does not go in evenly, neither the quotient nor the divisor can be factors, and the remainder is sometimes written as a value over the divisor. So one of two things can happen. Either it goes in evenly, so like 30 divided by 5 is 6, so it goes in evenly, and we see that 5 and 6 are factors of 30, because 5 times 6 is 30. Or when it doesn't go in evenly, neither the quotient nor the divisor are factors. So for example, like 30 divided by 7, when I divide that out, I get 4. Sometimes they'll write that remainder of 2, or 4 and 2/7 with the remainder over the divisor. But what does that really mean? What does 4 and 2/7 mean? Let me pause. All right, I kind of forgot where I was, but I think I was saying that 30 over 7 is 4 with a remainder of 2, or 4 and 2/7, or 4 plus 2/7. And interesting thing happens here. If you multiply everything by 7, you get that 30 equals 4 times 7 plus 2, which is kind of obvious, but this is important. Then in either case, whether it be something with a remainder or something without, you can always write the dividend as the sum of the product of the quotient and the divisor added to the remainder. So you can always write it, the dividend, in this case 30, as the sum of the product of the quotient and the divisor. So the product of the quotient and the divisor, 5 times 6, plus the remainder, in this case 0. Or 30 equals 4 times 7, quotient, divisor, remainder. And you can always do that. Well, that idea is kind of important. So based on this fact, we have the following theorem. For any a greater than b, with a and b being integers, there exist integer values for q and r that satisfy the following equation. Basically, if you have an a and a b, I'm saying let a equal 25 and b equal 4. Is a greater than b? Yes, it is. So there should be a way of writing 25 as 4 times something plus something. A equals b times q plus r. A equals b times q plus r. And it's very easy to find that q and r exist. I take 25 divided by 4. I get 6 with a remainder of 1. And so therefore, I see that q is 6. That's the quotient. And the remainder is 1. 25 is equal to 4 times 6 plus 1. This is a big idea in number theory and leads to the discussion of Euclidean algorithm method of finding GCD and of finding linear combinations. But that's not that important here. Just the idea, what I want you to get here is the idea that you take something, you divide it, you get a quotient, you get a remainder, and that quotient, divisor, remainder, and dividend can be expressed like this. Dividend is equal to divisor times quotient plus remainder. Okay? And guess what? If it's true for numbers, it's true for polynomials. Since polynomials act like numbers, in fact, numbers are polynomials. Let me prove that real quick. Take 532. 532 is really 5x squared plus 3x plus 2 when x equals 10. So just a thought. Okay, so every polynomial, or every number is in fact a polynomial. So if it's true for numbers, we can see it's true for polynomials. So this existence idea is extended to include them, and we see this. For p of x and d of x not equal to 0, so you got two polynomials, a polynomial and a divisor, not equal to 0, and the degree of the polynomial has to be larger than the degree of the divisor, there will exist unique polynomials q of x and r of x such that p of x is equal to d of x times q of x plus r of x. Basically the same thing I said before for numbers is now true with a polynomial. A dividend, dividend is equal to a divisor times a quotient plus a remainder. All right, so here's my example. I have p of x is equal to this polynomial, and d of x will say I'm dividing it by x plus 4. So therefore, according to this theorem I have here, or this idea, I should be able to write this polynomial as the divisor times a quotient plus a remainder. All right, so let's just show that that's true. So I need to find this quotient and this remainder. How am I going to do that? Well, with a linear divisor, I can use synthetic division, right? So instead of using 4, I'll use -4 because that is the 0 of the divisor. And I'll use the coefficients 1, -2, -29, and -42. And I get 1. 1 times that is -4. -4 times that is -6. -6 times -4. Positive 24. 24 -5. -5 times that is positive 20. Adding 20, I get 22, -22. And that is our remainder. So therefore, it's saying here that my polynomial p of x is really equal to x plus 4 times x squared minus 6x minus 5 plus -22 or minus 22 because that was my remainder. Okay. Okay, what I did real quick just to show it a different way is there was synthetic division over there. Then I did the same thing using long division. And you can see I got x squared minus 6x minus 5 minus 22 over x plus 4, or with a remainder of -22. So we see it works. This theorem, this idea is true that you can take a polynomial and write it as a divisor times a quotient plus a remainder. Now, an interesting thing happens. When you take a 0 of the divisor, or a 0 of the quotient, but we'll do a 0 of the divisor because it's obvious. The 0 of that divisor is -4. And you evaluate p at -4, you get -4 plus 4 times this quantity, which of course we could evaluate that too, but as I'm going to show you in a second, that won't matter because -4 plus 4 is 0. So we get 0 times this quantity, minus 22, or just minus 22. So it's interesting to note here that if you have a divisor and you take a 0 of the divisor, then the p of that 0 will equal the remainder. P of -4 will equal the remainder -22. And that's always true for any function, that if you put x up here, and this is f of x down here. And the reason that is because of this right here. Because when you put in a 0 of a divisor, the remainder you get at the end. This part, the 0 of the divisor will cancel out this term and that term, and you'll be left with a remainder. So that's a very important property, that p of the 0 of the divisor, we'll call it little r, okay, is equal to big R, where R is the remainder, okay, when you divide by R. Anyways, let me stop there and I'll continue in a moment.